The idea here behind the definite integral. All right, so let me draw just some random squiggle. All right, something like this. So let's say that this point over here is 0, and this point over here is 10. I don't know, whatever. Okay. All right, so what's the idea behind the definite integral? So what does this, and this is some function, of course, f of x, mean? How should we interpret it? Yeah. Yeah, so it's area, and I'm going to put a word here, net area between curve x-axis x equals 0 and x equals 10, right? So the x equals 0 and the x equals 10 tells us horizontally what we're working with, and then the function tells us vertically what we're working with, right? Okay, so I say net area here because, so there's some area there that I've shaded in blue, and some more over here, and some more over here. Okay, and then there's some area that I'll shade in orange that's below the x-axis. And if I said, what's the area of the orange region, right? Okay, with this shape, who knows what it is? But like, let's say I drew like a box, you know, something really easy underneath the x-axis. Then you'd look at it and you'd say, okay, well, I know some geometry. I could figure out it's 3 units or whatever, right? But how are we going to count stuff that's below the x-axis? Okay, so it doesn't make sense geometrically to talk about negative area. Okay, so this is more about our accounting than it is about the actual geometric area. Okay, so the convention that we'll use is stuff above the x-axis counts positively, stuff below the x-axis counts negatively, and if we wanted to know the actual just like total area, we could always throw an absolute value sign on stuff to sort that out. Okay. Okay, so that's why I said net area, right? So there I'm sort of thinking like when you guys talk about like say in economics, right, or something like that, right? What is like profit, say? Yeah, money coming in minus money going out, right? And here, right, the stuff that's going out, if you will, is the stuff that's going to be below the x-axis, that area, and the stuff above is the stuff count positive. Okay, so that's the bright idea. Okay, so let's look at then. All right, so the question is, how do you actually calculate one of these things? Okay, if the curve is like this, oops, come on, there we go. So like I drew this random squiggle here. Do I have any idea numerically what these areas are going to be? No, okay. I also don't know the function. So I could maybe approximate it, like let's say I printed this out on really, really fine graph paper and I could sit there and count the squares and kind of get a rough estimation of it. But if the function is anything, you know, sort of non-trivial, then it's not immediately obvious numerically what these values are going to be, okay? Unless we can use some geometry, okay? So, for example, let's say that I drew the following function. Okay, actually, you know what? Let me make it, let me change the radius just to make the arithmetic a little easier. Okay, so if I've got this here semicircle, right, and so let me just call the function that describes that f of x, and we could figure out the formula, but I don't really care right this moment. Then S would represent whatever that blue area is. Right? Now, because we all passed middle school, what is that blue area? How do I calculate it?
Pi over 2.
Okay, it's pi times,
R squared.
right, radius squared, okay? And then it's over 2 because it's only half the circle, right? I'm just doing the top half, okay? Now, what's the radius in this case? I made it 1 just for convenience of arithmetic, and so we get pi over 2 units. All right, so if the shape is something that geometry makes it obvious, well, then we're in great shape, right? We just use our heads. Okay, and then similarly, if I had, let's say g of x here, and this would be 3, and let's say it's also a semicircle, what would 2 to 4 of g of x be? Just 2 to 4. So just, yeah, it'd be negative pi over 2. Same area, but in the negative. And then if I were totaling the whole thing up, in this case, what would happen? They'd perfectly cancel and we get 0, okay? So it's certainly possible that you get 0 as one of these answers, even though this area clearly is not 0, right? It's just that it's net 0 because half of it's above and the other half is below. It's also possible that, like, they don't perfectly cancel out, and so you get, like, a really small number, even though the area looks really big, right? That could happen. In this case, just for sake of example, I made them perfectly total up. Okay, so let's look at the first one on the sheet here, right? And let me just kind of sketch the, oh yeah, grab one of those. Sketch this thing, right? So we've got 1 and 2, negative 1, negative 2, 1, 2, so it comes up to here, and then it goes across for 3, 4, goes across, and then it comes down, and then it goes down 2, and then it comes 7 and 8, and then it comes back up. Like this. Okay, so we've got a couple of different definite integrals to figure out here. So let's take the first one, 0 to 4 of f of x dx. Okay, so maybe the first thing to do would be, let's shade on the figure what area are we actually talking about. Okay, so what am I talking about here? If I'm going from 0 to 4 with this function, it would be this stuff. 1, 2, 3, 4. A little further. Okay, so what is the area of that stuff? Okay, and how did you compute that? Okay, that certainly works, right? To subdivide it into, we just put a big old orange line down the middle, right? So we have a rectangular piece, in this case happens to be a square, and we have the triangular piece, okay, which is fortunately a right triangle, so we don't have to do any weird trig nonsense. Okay, so what's the area of the square part? Well, that's easy. 4, okay. What's the area of the triangular piece? 2. And so the total of this thing is 6. Great. Okay, so why don't you guys do the other 3 parts, B, C, and D, and then we'll discuss. All right, so B was 4 to 6. C was 0 to 6, and D was 3 to 8. Okay, and subject to my crappy sketch, but it should be the same as the dude on the sheet. Okay, so take a minute and work that out. All right, so when you've got them all, put your hand on your head. Instead of doing the cup business. I'm so looking forward to this fall being like normal again. Because I don't know about you guys, but I'm tired of all this crap. No? Could make you hop on one foot and rub your tummy while you're patting your head? No?
Not that coordinated.
No?
Sir,
Yeah, well. All right, so what do we get for B? Well, first off, forget the number. I've shaded some stuff here. Which one is B's in terms of the shading? Huh? Yeah, it's the red stuff, okay? And in this case, what is true about the red area that's above the x-axis and the red area that's below the x-axis? Okay, so like I've got some stuff up here, right, and some stuff down here. What's true? Yeah, they do, in this case, perfectly cancel out. Okay, so what is this integral? Yeah, it's 0. Okay. All right, now, part C, in terms of the shading, what areas or what colors are involved in part C? Yeah, it's the red part and the blue part. Okay. Now, does it make sense that this is equal to let's think about why that's true. Right? Forget the numbers, right? Why does it make sense, no matter what the function is, that what I wrote down here is true? There's maybe a lot of ways to say this. Yeah, Nolan. Right, like I'm just splitting it into two chunks, right? The area between 0 and 4 and the area between 4 and 6. And like it almost is stupid when I say it, but I know it's a huge shocker. The area between 0 and 6 is the same as the area between 0 and 4 plus the area from 4 to 6, right? Because they cover the exact same chunk of stuff. Okay, so in this case, oops. Oh, that was weird. Okay, goes to the machine. In this case, is there anything really new to calculate? No, because we already know what this number is, and we already know what that number is, and using our thinking noodles tells us that the answer we want is just the sum of these two things. Okay, and so what do we get from 0 to 4? 6. What do we get from 4 to 6? 0. And last time I checked, 6 plus 0 is in fact 6. Right? Okay, so in this case we get the same answer. Okay. Question, preguntas, Fragen. Fragen? Nein? Question? Non? Oui. No? Okay, good. So, and then the last part, D, what was that one? 5 to 8? Okay, so in terms of my sketching here, I'm sorry?
3 to 8.
Did I write the wrong thing? Oh, yeah, 3 to 8, sorry. Okay, 3 to 8. Okay, so 3 to 8, in terms of my sketching here, what colors are involved? Well, definitely the red and the green part. And then what about on the blue? Yeah, it's only part of it. So let me sort of pick another color here. How about, well, the yellow will be kind of hard to see. How about purple? So 3, it'd be that part of it plus the red and the green. Now in this case, right, we already know what's the red area. So we can just ignore it, okay? And so then the only question is, what's the purple part and what's the green part? And what's the purple part? 2, okay? Base 1, height 2, it's a rectangle, great. And then the green area is geometrically 2, and therefore how do we count it? Negative, because it's below, right? And so what happens to that one? Yeah, it's 0 because the purple part and the green part just so happen to perfectly cancel out. Okay, and the red part it canceled itself out, I guess. Okay, so, right. So the question, right, and notice when I asked what's the area, Alex responded 2 for the green part. And that's true, that does have area 2. Okay, but what's the integral, which is to say how do we count that area? It's actually negative 2, right, because it's below the x-axis. Does that kind of distinction make sense? Yeah? No. James, did you get a haircut?
Yes, I did.
Did you get multiple hairs cut? Many? Okay. All right. I know, that's dad joke 101, right? So, okay, so does that kind of make sense? All right, so let's do the same thing here. Look over on the next page. We've got another graph that's a little bit more exotic. It's still built out of straight lines, so it's a function like this we would call piecewise linear. So figure out the other ones, and then we'll discuss. 5. And C was 0 to 8. Okay, so again, some just more geometry, but we'll consider this one the take off the training wheels version. So when you've got A through C, do the hand on your head bit. S'il vous plaît. You can do both hands.
Oh, yeah.
Yeah.
It's comfortable.
Dr. McKinney, take the wheel. So actually, let me make some more space here. All right. Well, let's look at A. Okay. So the area in A that we're looking at, right? It's built out of two pieces, right? One of them is a really tall triangle that's below the x-axis, and the other one's a nice isosceles triangle above. Okay, so it's, let me just draw it like this. It's this plus that. Okay, what is the part that's below the axis? Well, area-wise, what is it? I'm sorry? Yeah. Okay, so area 2, but counts negative because it's below the axis. Okay, and how'd you get that? Well, right, so what's the area of a triangle? Sorry, let me back up a minute. Right, okay, so the base in this case is 1 and the height is 4. So the area is 2, and then it's negative because it's below the axis. Okay, what about the isosceles triangle? Base 1, height 1, therefore area is 1/2, right? And so in this case we get negative 1.5 or negative 3/2 if you prefer fractions. Did you guys know that 9 out of 3 Americans struggle with fractions? Yeah, that one's a pretty good one, right? Or this is one that I couldn't make until I moved here to this part of the Midwest. Every time I go up to Lafayette and I see a Fifth Third bank, like a part of me dies on the inside. I'm just like, I don't trust a bank that can't like Fifth Third, and like their logo actually is a fraction with 5/3. Yes. Like no. I mean, I feel like whenever I see it, I'm like the Jackie Chan meme with like, you know. Well, you guys can't see my face when I'm doing that, but you know what the meme is, right? Yeah. So anyway, okay. So good. What about B? So B was 3 to 5. Okay, and what pieces are involved there? Well, how'd you guys choose to decompose that? There's a lot of ways that you could have done it. Yeah, what'd you do? Okay, that works. How else could you decompose it? Yeah. Yeah, so there's like a rectangle and then a triangle sitting on top of it. You could have decomposed it into two trapezoids, right? There's a lot of ways you could have carved this thing up. But in the end, what did you get? 3? That looks reasonable. Okay. And then C was 0 to 8 of g of t dt. Okay. And so this was the whole shooting match, adding everybody up. Okay, and what did you guys get? -1? Agreement? Okay, good. Now, in particular, let me draw your attention to the part between 7 and 8. Okay, did we really need to go from 0 to 8, or could we have just gone from 0 to 7? They're the same thing, and the reason is, what's going on between 7 and 8 on this function? Yeah, the function is just actually flat out equal to 0, right? Okay, great. If the function is 0, what's the integral going to be? Because there's no area in between. Right, does that make sense? Yep. Okay, so yeah, that totally can happen. If the function is 0, then of course the integral is going to be 0 because there's no area to add up. It's basically asking, what's the area of a rectangle that has no height? Well, yeah, it's sort of a stupid question, but the only reasonable mathematical answer would be 0. Okay, okay, so let's look at the next one here. So there are 6 problems, and they continue on the next page. Okay, so the first 2 that we did, the function f and the function g, we were able to do that because we had a graph in front of us. But what happens if we don't have a graph in front of us? You either make one or use your noodle. Okay, so now we have to make the graphs. Okay, so take a minute and work out, well, let's start with A and B. Okay, so let me just divide you guys up here. A, B. Alex, A, Owen, B. A, B, A, B, A. Okay? Since they're the same function, right? And then we'll look at the other 4 because they're a little different. Okay, so what's the first problem in A and B? What's the graph of absolute value look like? Hopefully you guys remember that one. Right? And, oops. Well, actually, I'll write this in a minute. We'll look at it a second way. So hand on your head when you've got your part worked out. We'll see what the crew thinks, the squad. right, looks like we're good. All right, so what'd you get for A? 0 to 2. 2. Okay, and because it's a right triangle, base 2, height 2, area 2. Okay, great. All right, what about B? 4. Okay. All right. Now, why is it 4 and not 0? Because it's above the axis, right? So this area over to the left is geometrically the same as the area over on the right, but it counts positive because it's still above the x-axis. Okay, does that make sense? All right, and then in this case, it just doubles. Okay, great. All right, now, with this particular function, let's suppose that we were just being really silly one day, and we just totally forgot how to graph absolute value of x. Could we have still done this problem? Well, hopefully, right? And so here's another way to do it that's completely ungraphical. All right, how is absolute value of x actually defined? It's defined as a piecewise function. Okay, do you guys remember what the definition is? Mm-hmm. Okay. Mm-hmm. Okay, and to be continuous, it's got to be defined at 0 also. And in this case, I've got two choices. I could either make the greater than into a greater than or equal, or the less than into a less than or equal. It doesn't really matter, though, because both of them are 0 at that point. Okay, and so the convention is that one, right? It's not going to matter for our purposes, but right, okay. So this is the piecewise definition of absolute value. And when did we use that? When's the last time we used that definition? If you happen to remember. Yeah, when we were talking about differentiability, and we said, okay, what's the derivative of this function at 0? And we were trying to argue why it didn't exist. Okay, and what did we have to do? We had to say, well, if we're thinking about a limit as x approaches 0, or any other number, right, for piecewise defined functions, where's the potential problem? On the border between the two definitions. Okay, in this case, that happens at 0. And so we said, okay, let's do the left-hand limit, and let's do the right-hand limit, and let's see if they come out to be the same thing. And in the case of this guy for the derivative, they did not, and so that's why we said it wasn't differentiable. Okay. Now, you could have also sort of saw that geometrically, because what were the slopes on the right-hand piece? The slopes of the tangent lines? 1, okay, positive. And what about on the left-hand side? Careful. -1, okay, the slopes, right? And how do I go from -1 to 1, right? At that point at the bottom, I sort of want the slope to both be 1 and -1. Well, can it be both? No, that doesn't make sense, right? Okay, so maybe a good analogy for this, I don't know if I've used this one, is how many of you guys have like brothers and sisters that are, say, younger than about 12 or 10 or so? Anybody? Yeah. Okay, so do you ever find yourself with sort of child babysitting / supervisory duties when you're at home? Every waking moment. How many do you have? Huh? Okay, older sisters. Yeah, so you're definitely from a Catholic family, aren't you? Oh, and you too? Right, okay. So, great. So what happens if they're fighting over a toy? Right, what do you do if they're fighting over a toy? Okay, Yeah, you first see if they can arrange a sharing agreement, right, or something along those lines. And if that doesn't work, then what? You do the nuclear option.
Take it for
Neither gets the toy. Okay, so it's kind of the same thing here, right? Half of the function wants the derivative to be 1. The other half wants it to be -1. They can't agree. So sorry guys, I'm taking the ball away. Okay, so that's the last time we had to use this definition, but we could use it here, okay, because if I'm asking what's this, I could say this is the same, well, here, let me write it this way. Yeah, wow. I could do that, right? That was sort of the, if I can, well, I'm splitting the integral, right? I'm saying, okay, it's the left-hand piece plus the right-hand piece, and then I'm just adding the two together. But by splitting it that way, this one is that, and that one is this, okay? Because if I'm on the interval from 0 to 2, what is absolute value of x? What is its definition? So I go up to my piecewise thing. Is 0 to 2, are those numbers bigger than 0? Yeah, so the function is really x, so I replaced absolute x with x. And then what did I do on the negative part? Yeah, it's negative x, okay? Well, if you manage to stumble your way into a calculus class and you don't know what the graph of x or negative x looks like, we have a problem, okay? But, yeah. Okay, so that's another way that we could have done this. Cool? Okay, so flip over to C, D, E, and F. All right, and I want to draw your attention to, well, okay, is D going to be tough? Why not? Why should D not be theoretically that hard? Yeah, it's a straight line, and the slope and the intercept are not that, not outrageous numbers, okay? So a crude sketch should be good enough to get those. What about C, E, and F? What's the problem there? Well, E and F are, but what about C? Right, we have to remember what the graphs of these things are. Okay, now, C, what does the graph of sine look like? Do you guys remember? All right, at pi halves it hits 1. At pi, it's back down to 0. And I've made it look kind of circular, but it's not. Let me draw it a little bit more like this. Okay, and then what is it going to be, therefore, over here? Okay, so in order to do this, for now, the only tool up our sleeve is the graph. Okay, all right, now, E and F. Yeah, so what was the magic word you said there? The circles, or semicircles, right, in this case, or quarter circles. Okay, so y equals, let's just take both pieces here. Let me do this one. Okay, what is if I graph this thing, what would I get? I'd get a half of a circle. Okay, is it clear just looking at it that it's a half of a circle? Well, maybe, maybe not. Okay, but what about if I square both sides and I move the x squared over? Now it should be dead obvious it's a circle. Right? Because I've got x squared plus y squared equals radius squared. In this case, just conveniently, it was centered at the origin. That's nice. Okay, it didn't have to be, obviously, but it's certainly nice that it is. Okay, so this is maybe a little bit backwards. So like think back to high school. If you had the equation of a circle or, something else, right? X squared plus y squared equals 9, and you wanted to graph that on your calculator, what was the problem? I'm sorry? Yeah, exactly. That's not a function. It's a perfectly good equation, but it ain't a function. Okay, and if you wanted to use your TI whatevers, then what did you need to do? You had to first express it in terms of y, right, so that you had a function to graph. Okay, and what would you have done? You would have basically done the steps that I wrote down, but in reverse order. Okay, and then with one minor addition, if you went the other order, what technically do I need to throw in front here? Huh? A plus or minus, because there's really two parts, right? There's the top half of the circle, that's one function, and the bottom half of the circle is the other function. Okay, does that make sense? Okay, so for E and F, well, first off, why don't you guys take a minute and work all four of those out, and then we'll come back together. Oh my, how time is flying. Right, when we're doing peace, love, and calculus. I don't know, what do you guys think? Would there be more wars or fewer wars if there was more calculus in the world? More calculus. More wars? What about if there was less calculus? Huh? They'd be at war with themselves. Yeah. All right. Well, so this sine function, what just so happened to happen in this one? They cancel out. So what's the answer? 0. Okay, that's coincidence. And in fact, if they didn't perfectly cancel out, we wouldn't be able to do this problem with the tools that we have at our disposal yet. Okay? Because the graph of the sine function, it's not a circle or any other shape that I have like geometry I could throw at it. Okay? Now contrast that with E and F. Okay, so E, first off, let's sketch which half of the circle am I looking at, the top half or the bottom half? Top, because it's a positive square root, not the negative. What's the radius? 3. Okay, and which piece of the circle am I actually interested in here? That's told to us by the bounds of the integrals, the number at the top and the bottom. I'm sorry? The part in quadrant 2, which is that quarter circle. Okay? So, what's the area formula for a circle? Okay? And in this case, we only have a quarter of the circle. And what's the radius? 3. Okay, and so we just get 9 pi over 4, whatever. Okay, okay, does that make sense? All right, what about an F? Which part of the circle are we thinking about? Top half or bottom half? Bottom half. And in that case, do we have a quarter circle, half circle, something else? Half circle. What's the radius? 5. Okay, so what would the area be? Right, negative 25 pi over 2. So the area is 25 pi over 2, and then therefore the integral is negative that because it's below the axis. Okay, good? Okay, so we talked about some symmetry. Now let's look at these sort of properties real quick. We already did part C. Part B, just just take that on faith for right now. Part A, if you integrate from A to A, that's like having a rectangle whose width is 0 instead of its height. What do you think the area of that's going to be? Right, that makes sense. Okay. All right, and then if we flip over to the very back there, okay, if do you guys happen to remember the definition for a function to be odd? It's this. Okay. So a function is said to be odd if f of minus x is really the same thing as negative f of x. Okay, in terms of the graph, do you guys remember what kind of symmetry the graph would have? Okay, so what kinds of symmetry could a graph have theoretically? Could have x-axis, y-axis. What was the third one? You guys remember? Starts with an O. Ends with an N. It has a regia in the middle. Origin. Okay, to get ringing a bell now? Right. Okay, so these things have origin symmetry. Okay, now, but if we think about this, if f of minus x is sort of reflecting about the y-axis. So if the stuff on the other side of the y-axis is negative of what it is on the other side of the y-axis, what do you think the integral is going to be if we integrate with something that's symmetric about 0? It's going to be 0, okay? And the reason is plus. This part, by the function being odd, would be negative the integral from negative a to 0 of, 0 to a. And they cancel out, okay? Okay, so if you guys could do me a favor then, take a few minutes and put your thinking cap on for part E, and we'll start with that first thing on Friday, and then carry on, okay? All right, well, thanks for playing. Yes?
You had to talk about like that just dropped off that shows that.
That what now?